Hello everyone. In this video, we will continue our discussion of two-body potentials or pair potentials. Just as a reminder, we were discussing uh, two-body, sorry, two-body potentials, and so far we covered in a previous video the Lennard-Jones potential. And today, we said that the Lennard-Jones is mainly to describe van der Waals interaction. In this video, we'd like to discuss Buckingham potential. The Buckingham potential is supposed to describe both van der Waals and uh, uh, the electrostatics. And because of this, this particular potential is suitable for ionic materials, especially the inorganic ones. So generally, this is used to describe ceramics, such as oxides, maybe carbides. Although carbides, they have some covalency, and you probably need something extra beyond the Buckingham interaction. But let's say oxides, they are genuinely ionic materials, and as such, it would be successful in describing such materials. So for example, this could describe magnesium oxide, uh, where formally in magnesium oxide, magnesium cations are +2, and the oxide ion is 2-. It could also describe salts, for example, crystals of salts, of course, like sodium chloride, right? Again, formally, sodium is +1, and the chloride ion formally is -1. And notice that this is the case. This would be a good potential to describe sodium chloride in its crystal form, not really into aqueous solution form. Or I shouldn't say this. I should say it's not common to use Buckingham for aqueous, for sodium chloride ions dissolved in water, for example. What is the formula? What is the equation for this? Again, it's a two-body potential, so it depends only on the distance between these two ions. V of r equal some constant A exponential negative the distance r divided by rho minus C over r to the power 6 plus the electrostatics part, which is Q1, the first charge, Q2, the second charge, over r. And now let's take a second to look at these terms. This is supposed to represent short-range repulsion. Short-range repulsion. Remember, this is similar in Lennard-Jones potential, similar to the r power 12 term, right? So this exponential is supposedly to replace the r power 12 term in Lennard-Jones potential. The r power 6 term is exactly the same as what we have seen before in Lennard-Jones. So this is supposed to represent long-range attraction. Long-range attraction, or that's pretty much really the van der Waals description. So in a sense, Buckingham, the first two pieces of Buckingham are very similar to Lennard-Jones, except that the r power 12 is replaced by an exponential function here. Now, the new thing is the electrostatics, and this is pretty much Coulomb's law, so nothing really fancy. First charge, second charge over the distance. I have to say something here. What are the fitting parameters? Like, suppose you want to develop a Buckingham potential for certain ionic material. What would be your fitting parameters here? So the fitting parameters will be A, rho, so this constant rho, C, this little c here, and actually Q. So you need to fit A, rho, and C, and Q. So Q is not necessarily the formal charge from chemistry, like +2 for magnesium or 2- for oxygen. Instead, you might actually use a partial charge. Especially this would be the case for some material that's not fully ionic. In that case, you might reduce the charge a little bit in comparison to the formal charge. But one has to think about how many of these you have. So suppose you are studying, let's say, magnesium oxide. Then you would expect that there is A rho C for magnesium, 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 C magnesium, magnesium, and Q for magnesium. Similarly, you would have A for oxygen, oxygen, rho oxygen, oxygen, C oxygen, oxygen, and Q for the oxygen ion, the oxide ion. And finally, there will be also A for magnesium oxygen interaction, rho magnesium oxygen, C magnesium oxygen, and of course, the Q have been already covered in the previous lines. So in a sense, if you have an oxide made out of two, of a cation and an anion, you have about, how many here? We have 11 fitting parameters. So that's actually a lot. However, wisdom has shown that there is really no need for the cation-cation interactions. So these are usually absent. Of course, the Q will remain. I apologize. The Q has to remain, but the A rho C for the cation usually has been ignored, claiming that it doesn't play a major role in the interactions in ionic materials. And as such, we are left with the two partial charts and the 6 A rho and C for the anion and anion cation, right? So that actually reduced the fitting parameters space into 8 parameters. So you see, even such a simple interatomic potential still actually leads to a large fitting problem. Now, and something similar to what we have discussed about Lennard-Jones, we cannot apply this potential forever, right? We have to have some cutoff distance. And here there is a peculiar discussion, especially for the Coulomb part, the electrostatics part. So this is the Coulomb part of the interaction. So let's make a comment here. So cutoff. Typically, one applies an R cut of also about 10 angstrom. Again, you have to go back to the paper from which you obtained this potential. And this is usually applied to the exponential term and to the R power 6 term. Now, for the electrostatics, the Coulomb part, you cannot really apply simple cutoff. Like you cannot cut the 1 over R term. The electrostatics, remember, the electrostatics is the 1 over R. Mathematically, the 1 over R series cannot be cut at some finite number of terms. In fact, it has to be summed all the way to infinity. But again, how would you do this? The trick is really elaborate, and we will not go into it. The mathematics are really involved here, so we will just describe the idea conceptually. Usually, we apply a technique called Ewald sum, or a derivative of it, some simplified form of it. Again, this is not really the topic of the discussion. If you are interested, you can search about calculating electrostatic interactions. But let's describe the idea in brief. In brief, it is the following. Starting, let's put the R line here. Starting from 0 to, let's say, 10 angstrom, we usually calculate the electrostatic interaction in real space. In real space, that simply means using the formula in the previous page here. If we go back, it's the 1 over R term, Q1, Q2 over R. Of course, there is epsilon note and everything. We are just using some sort of simplified units here. There is still the dielectric permittivity of vacuum if you apply SI units, but again, we are not really here discussing the units. But then how about from 10 angstrom, all the way to infinity? This is not calculated in real space anymore. This is calculated in reciprocal space, or the Fourier space. If you think of it mathematically, this is like a Fourier transform, where you go from real space to reciprocal space. In reciprocal space, 10 angstrom actually corresponds to 1 over 10 angstrom minus 1. That's in reciprocal space, right? It's 0.1. Meanwhile, infinity in reciprocal space actually corresponds to 0. So this is 0 angstrom minus 1. So it's like you are going in real space from 0 to 10, and in reciprocal space from 0 to 0.1, and then you sum the two contributions together, and that's the technique of Ewald sum, right? The technique, as I said, is very elaborate mathematically, but it's really beyond the scope of the discussion here. Pretty much all the software that does molecular dynamics or interatomic potential calculations, you will have a utility coded already to do the electrostatics calculations for. So that's with regard to the cutoff. There is another 2 points that deserve discussion for the Buckingham potential. So we are done with the cutoff. The second point is what happens if the limit of R goes to 0. That's actually the very, very short range. You might think that this is, well, come on, this is very, very close distances. So one imagine that the electrostatic potential will, V of R as a function of R should be shooting up, very, very, very up, very repulsive. The problem is, if you go back to the interaction here, take, for example, sodium and chloride, or magnesium and oxygen. So this term is negative. So this is attractive. So this is not going to give you a positive component, right? And in fact, this term is also negative because C is always a positive constant. So this will be negative. So this is always attractive. And in fact, as we go to infinity, to 0, C over R to the power 6 with a negative sign will give you negative infinity. So let's actually do this calculation here. It's not a calculation, it's a limit. So let's say sodium and chloride, so positive anion and cation. So the 1 over R term will go to negative infinity, right? So Q1, Q2, thanks to the Q1 and Q2, it's not really the 1 over R, it's the Q1 and Q2 that gives you the negative sign. Similarly, the minus C over R to the power 6 will go to negative infinity. So that means that your only hope to get a repulsive interaction, if you go back, is the exponential term. But unfortunately, it will fail us. Why? Because if I substitute here with R equals 0, exponential, obviously this is a positive quantity, so exponential 0, that's actually 1, you will be left with A, and A is a positive number, but it's not infinity. So in the limit, so let's go back, in the limit, A e to the power minus R over rho will actually go to A. So let's see, we have 3 terms, 2 of them to go to negative infinity, and 1 term go to a finite positive number. So the totality of the interatomic potential will actually go to negative infinity. That means that unfortunately, at very, very, very short distances, Buckingham potential turns down wrongly and give you a negative interaction, negative, which means attractive. So that means that if you have sodium and chlorine, sodium cation and chloride anion, and you bring them very, very close to each other, in fact, according to the Buckingham potential, they will attract each other. The problem is not severe in most of the calculations. In fact, pretty much all the usual or everyday calculations, they are usually in the region where the Buckingham is still positive in totality, of course. The sum of the 3 terms is still positive at short distances for a cation and anion. Only at very, 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 very short distances, and this depends on the actual numbers of A, rho, and C, and the Q's, of course, very, very short distances, it actually becomes attractive. Now, what kind of simulations this will become problematic? This is usually problematic in radiation damage studies. in radiation damage, and I refer the interested reader to the wide literature on this topic. Usually we are interested in what happens when we bombard the material by a projectile, let's say a neutron or some big atom like carbon atom or helium atom. In radiation damage, you do this bombardment, and thanks to this huge kinetic energy due to the bombardment, you might actually get sodium and chloride to very, very short distances. There are ways to treat this issue. You can even add an extra term at very short distances, but again, this is really beyond the scope. It's just important for us to recognize what are the limits of the terms in Buckingham as we go to R equal, as we go to R tending to zero. Now, final comment on Buckingham, which is related to polarizability. Polarizability of especially anions, I would say. Anions, like the oxide ion, for example, they tend to be fluffy, as you can see. Their outer electrons are a bit fluffy, and this generates some sort of, some net dipole moment while they are existing in their own materials. Same thing goes for nitrogen, chloride, so nitrogen, chloride, and so on. All these anions, they tend to be fluffy. And this fluffiness can be modeled with a very, very simple model, simple mechanical model. It's the so-called core shell model. I will give other names for this because it's actually existing in literature under various names. But in the core shell, we usually represent an atom, an anion such as the oxide ion, by a positive species. Usually, it represents the nucleus and some core electrons around it, plus some core electrons, and another particle. So this is usually called the core, and another particle called the shell, and they are connected by a spring. So there is a mechanical spring that connects them. The energy of the spring is very simple. It just applies to the core and shell within the same ion. It's like half k r minus, r squared. So there is a spring constant that needs to be fitted in developing a core shell model. And as I said, this is only for the anions. It's very rare only in the old literature people try to do this to cations. But again, cations polarizability are not that big, generally speaking. And there are some exceptions, of course, but we are unaware of some recent models that try to model them with this approach, like the bismuth cation, sorry. But traditionally, this is the case for anions. Now, for example, if the oxide ion is gonna be set to formally have a charge of -2, so you might have a core that's actually plus 0.4 and a shell that's -2.4, which gives you in totality the -2 here. Of course, the division of the charge among the core and shell is also one of the parameterization of the interatomic potential, which the developer of the potential need to fit. The model is actually very old in physics. It goes back to a very old paper to Dick and Overhauser. And I believe this is some 50s paper. Not exactly 50, but it's like 1950s paper. In biological matter, the very same model have another name. It's called Rode model. This is the literature in physics and material science. It goes under this name, Dick and Overhauser core shell model, while in bio, it goes under Rode model for polarizability. And some of the famous interatomic potentials in biology, they are actually force fields in biology. They are revised again to account for these polarizabilities. For example, the charm force field for bio matter, like for proteins and carbohydrates and so on, is reparameterized by its own developers to, to account for these polarizabilities of the anions. Now let's go back and recap what we have covered in this video. We discussed a second two-body potential, which is the Buckingham potential, usually good for ionic matter, especially inorganic. It goes with three terms: exponential to represent short-range repulsion, um, minus c over r to the power 6 to represent long-range attraction. This is a van der Waals part, and it's very similar to Lennard-Jones, and a third term to represent electrostatics. This leads to a wide set of fitting parameters, especially the charge here. You might actually use partial charge for the fitting process. A couple of comments on this interatomic potential. In terms of cutoff, the first two parts, the exponential and the r power 6, they can be cut at some cutoff distance, typically 1 nanometer, but one has to check the paper that developed the potential. While the electrostatics part usually goes to infinity, or practice otherwise, this actually doesn't really represent ionic materials. And then the way to do this is via an algorithm called eval somewhere. Divide the effort into two pieces, real space and reciprocal space, and you sum the two components at the end. One major problem in Buckingham potential is when you go to the limit of r equals 0, which is relevant radiation damage. Unfortunately, two terms go to negative infinity and one term go to a finite positive number, and the totality of the potential goes to negative infinity, leading to net unphysical attraction at very short distances. There are ways to treat this, but unless you are really studying radiation damage, it's not really a problem in most everyday calculations. And finally, you can actually describe the polarizability of anions. So this is on top of Buckingham. Like you can think of, there is magnesium here, an oxygen here, and another magnesium, and another oxygen. But this oxygen is described by two parts. You see, is described by two parts, describing the polarizability. Is via the core shell model, where there is a positive core representing the nucleus and the surrounding core electrons, and a negative shell to represent the outer electrons. The core and shell inside one unit are connected by a harmonic spring, something very, very simple. And surprisingly, such a simple model is capable to represent the polarizability of anions. In physics, it goes under the name Dick-Overhauser core shell model. In biology, it goes under the name Drode model. Thank you so much, and see you in another video.